Hello my dear learners, as we are going through the subject antenna and wave propagation since last many lectures, today we will discuss some very important topics in the form of some theorems in electromagnetic field theory, Laplacian of a scalar, curl of a vector. Basically, these are the topics which we have already discussed in our previous lectures, but the significance and the interpretation, actual interpretation in the electromagnetic field theory and antenna and wave propagation, we will discuss today. How these operators like divergence, gradient, curl, these are the operations of a del operator, and these operations play a very vital role in some of the applications in electromagnetic field theory. It is very important to discuss these theorems, the operation of the curl, Laplacian, divergence, gradient, all these operations are very important, because through these parameters we can calculate the field radiation. In my next few lectures, as we will proceed the electromagnetic field theory and antenna and wave propagation, we will see that electric field and magnetic field, both are the fields which are the significant in the space, and when the output of these two fields is calculated through a conducting element, it comes in the form of electromagnetic waves or electromagnetic radiation. So, today we are going to start some of the very interesting theorems, some of the very interesting operators which are important in the subject antenna and wave propagation. Okay. So, we are starting with the divergence theorem. As I have already discussed about the divergence. What is divergence? In my last lecture, I have briefly discussed the physical significance of this divergence. Actually, the name divergence theorem itself says something about the divergence. It means within this theorem, the divergence will be elaborated, the application of divergence will be explained, and this divergence says the flow, inward flow, outward flow. As we know that divergence is the quantity which we can measure for a flux of a field, for the flux of a vector, and this flux is, if in the form of outward flow, it is positive divergence, when it is inward, it is negative, and when the inward and outward flow of the flux is same, then divergence is 0. On the basis of this concept, on the basis of this physical interpretation of divergence, we can explain the divergence theorem, we can prove the divergence theorem, and in this slide the statement and the mathematical notation of the divergence theorem is given, and it states that the total outward flux of a vector field A at the closed surface S, it is the same as the volume integral of the divergence of A. As its mathematical notation says that double integral means the surface integral of the vector field A in a closed manner, it is equal to the triple integral, means the volume integral of the divergence of that vector field. This is the statement, this is the mathematical notation of the divergence theorem. How we can prove it? So, going in the proof of the divergence theorem, yeah, one more thing, that this divergence theorem is also called as the Gauss divergence theorem. As we know that this divergence theorem provides us the relationship between the surface integral and the volume integral. In this manner, we take a volume V. Suppose this is a form of a large number of parallelopipes are adjoined together. In the same way, consider a surface S which encloses a volume V, and let a vector field A be that particular vector for which we have to calculate the surface integral and the volume integral in this particular field. Let this volume is made up of a large number of elementary volumes in the form of parallelopipes, as you can see in the diagram. There are subdivision of the complete volume in part 1, part 2 and part 3. Suppose an elementary volume jth, which is a part of this complete volume of the vector field A, and when we consider this jth parallelopiped, which is having a volume of delta Vj, and this volume is bounded by a surface Sj, then the surface integral of that vector A over the closed surface Sj may be given in terms of this mathematical notation, which is given by double integral in the closed surface as vector A dot dsj. It means this dsj is the differential surface area of the jth element. Now, for the simplicity, the whole volume has been divided into elementary large number of volumes. As in the previous diagram, we saw that the complete volume was divided into part 1, part 2 and part 3. Here the outward of elementary volume 1 is the inward of the elementary volume 2, and the outward of the elementary volume 2 is the inward of the elementary volume 3, and so on. If we divide the complete vector field of A in large number of volumes, then it will continue like this. Therefore, the sum of integrals of elementary volumes, they will cancel each other, and when they will cancel each other, we will be left with the surface integral which arises from the surface of S only, and it can be written like that: sum of the double integral surface in the closed way A dot dsj is equal to double integral of A dot ds. It means when the sum of all the elements in that particular volume of vector field A will be summarized, will be summed up, then the calculation will be dealt with the complete surface area in the terms of double integral A dot ds. A simple mathematics is drawn here in the form of multiplying and dividing left hand side by the equation of this equation by delta Vi, and then we get that double integral of the A dot ds. It is equal to sum of 1 upon delta Vi and double integral of A dot ds it is multiplied by delta V I. Now, let us suppose the volume of surface is divided into multiple elementary volumes, so that delta V I tends to 0, and when it is 0, then this equation becomes like this, and when the final solution of these multiple equations we get like this, means our motto is that delta V I tends to 0, and when we put this value delta V I tends to 0, then we get that it is the final solution in the form of del dot A, and hence this equation becomes like this: double integral A dot ds, it is equal to sum of the del dot A into del V I, and this particular form of the equation can be written like this, that double surface integral A dot ds is equal to triple integral in the form of volume, and it is equal to del dot A into dV. This is the relationship between the surface integral and the volume integral, and this particular equation like this: double integral surface integral A dot ds is equal to triple integral of del dot A dV, and this equation is called as the Gauss divergence theorem. This is the significance, this is the proof, and by using the different mathematical analysis and by using different formulations also to prove this Gauss divergence theorem. But it is important, and we have to understand and we have to remember about the Gauss divergence theorem, that it is the relationship between the surface integral and the volume integral. When a vector field is divided into multiple surfaces and multiple volumes, then how we can justify the relationship between these two. So, this is the Gauss divergence theorem, and my suggestion for remembering this particular theorem, because in coming days, in coming topics, we will use this Gauss divergence theorem in electrostatics, in multiple, as this Gauss law is very important for the calculation of Maxwell equations. So, electromagnetic field theory, this divergence theorem, this Gauss divergence theorem is very important. So, remember this, and for remembering you can just remember that it is the relationship between the surface integral and the volume integral. Okay. So, coming to the next point, curl of a vector. Curl of a vector is a very important concept, as we already discussed about the curl. Curl is a cross product. Curl is a cross product of the del operator with a vector. Okay. So, the physical interpretation of a curl is always comes in the form of rotation, in the form of circulation. So, we can also justify this curl of a vector like that it is an axial or rotational vector whose magnitude is the maximum circulation of E per unit area, which tends to 0 and whose direction is the normal direction of the area when the area is oriented so as to make the circulation maximum. The overall therapy of this curl of a vector is the calculation of the maximum rotation about the axis, and when we denote this particular curl of a vector, it is like del cross E, and simply we can elaborate it in the form of different significance, like what is the physical meaning of this curl of A. This is the curl of a vector at any point, it is a vector because it is a curl operation. Then obviously, when this cross product is there, obviously the result will be in the form of a vector itself. So, curl is a measure of how much the vector curl around the point in question, and obviously this the result in the form of a vector quantity. When we take an example, we can say that when a rigid body is rotating, when we are talking about the rotation or the circulation, then we can say that when a rigid body is rotating about a fixed axis, then the curl of the linear velocity of a point on the body represents twice its angular velocity. This is the physical interpretation of the curl, how the curl is acting in the electromagnetic field theory or some of the operations on the vector field. Curl of a vector can also be represented in this form, like curl of E, it is del cross E is equal to limit ds tends to 0, line integral of E dot dl upon ds, and it is normalized in the direction of an. An is the unit vector in the normal direction, and its maximum value provide the curl of a vector. When we generalize it in the form of line segments, then this particular figure can be followed like this. Here the 4 segments are given and the complete line integral of the vector E is represented in the form of the separate integrals of the 4 line segments. So, it can also be represented for the curl of a vector E. As I have already told you, the curl significance in the form of rotation, in the form of circulation, it can be defined as the curl of a vector field is concerned with rotation of the vector field, and this rotation can be used to measure the uniformity of the field. It is uniform, it is non-uniform, the value of the curl is identifying this particular procedure. The examples are given here. There are 2 figures. In first, the field is uniform in the form of straight lines, and here the curl is 0, but when the field is rotational or it is circulating, then the curl is non-zero. This is a very suitable and very general example for describing the value of curl. Now, what are the basic things related to the curl? In the form of 3 coordinate system, this curl can be defined like this. In the Cartesian coordinate system, it is a very simple in the matrix form, like del cross A is equal to Ax, Ay, Az. These are the unit vectors in the x, y and z axis. These are the del x, del y, del z are the differential elements in the direction of x, y and z, and Ax, Ay, Az, these are the magnitudes of the vector A in the direction of x, y and z. And when we elaborate this complete matrix, it is in the form of del cross A. For the cylindrical coordinate system, this can also be defined like del cross A is equal to 1 upon rho, and in the matrix like this A rho, rho A phi A z. Here the unique thing is with the phi component. Phi component cannot be used separately or independently in the matrix form, because it is a angle. So, for describing a distance, a line or a segment, we have to use the radius vector which is multiplying with the angle. Okay. So, this is the explanation, this is the complete elaboration of the cylindrical coordinate system curl operation. This is a very important mathematical spherical coordinate system, because in electromagnetic field theory and antenna and wave propagation, this spherical coordinate system is most widely used. And for using this particular coordinate system, we assume that the complete radiation from a conducting element or an antenna it is spreading in the sphere. So, I suggest all the learners to learn to remember this complete mathematical notation to use further use in the EMFT and antenna and wave propagation. Okay. So, these are the physical interpretation of the curl. We have to understand all these interpretations, because by understanding these interpretations we can use in the antenna and wave propagation subject the curl operation. Vector field f that represents the flood velocity, and the curl of this f at a point in a flood, it is a measure of the rotation of the flood. We understand that if there is no rotation of the flood anywhere, then del cross f is equal to 0, and this vector is said to be the irrotational. For a two dimensional flow with f, it represents the flood velocity in the form of del cross f, and it is perpendicular to the motion and represents the direction of the axis of rotation. The curl also enters into the electrical engineering in the form of describing different parameters in electrical and magnetic fields. A magnetic field which is denoted by H, it is the property in the form of del cross H, and it is equal to J, the conduction current density. In the electrostatic field, this is also defined, the curl operation of E is also defined as the 0, which is known as the conservative field. Next come to the Stokes theorem. It is also a very interesting theorem, and this theorem provides a relationship between the line integral and the surface integral. You can see here that the circulation of a vector field f around a closed path L is equal to the surface integral of the curl of f over the open surface as bounded by L, that f and curl f are continuous on S. It is a condition that f and curl of f must be continuous on the surface S. The conditions, the limitations and the most suitable things are given in the form of Stokes theorem to generalize it in the electromagnetic field theory. The mathematical notation is given in the form of a vector field f, like this: line integral of f dot dl, it is equal to surface integral of del cross f dot ds. You have to remember this Stokes theorem. In the way as we have derived the divergence theorem previously, in the same manner, in the same way we can define the Stokes theorem proof, and a complete vector field A, and which is enclosed by a surface C, and it is defined here in the form of a curve C. Then the line integral of a vector A along the closed curve, it is given in the form of the closed curve C, and the closed line integral of A dot dl, it is defined only for the closed curve C, where dl is the vector of the length of a small element of the path given in the figure. So, by describing the different small segments, line segments, we can also show the proof of this this Stokes theorem. This figure, when this complete surface is divided into many small portions, the complete proof of this Stokes theorem is given in these equations. One by one all these equations are solved, and finally we get the result in the form of line integral closed loop A dot dl is equal to surface integral del cross A dot ds. This is the result of Stokes theorem, and we have to remember that it is the relationship between the line integral and the surface integral. Finally, we come to the very interesting and very important operator which is known as the Laplacian. Laplacian is the divergence of gradient. It is a composite of gradient and divergence operator, and this is the operator which is required everywhere to describe the radiation. Mathematically, it is defined as the divergence of gradient, and when we put this value del dot del, it means it is del square. So, the Laplacian can be denoted in the form of del square, and when we say that Laplacian of a scalar, then we can say that it is del square V. It is very important operator, and we have to use this Laplacian operator in all the kinds of coordinate system like this. Laplacian of a scalar field V is written as del square V, where the Laplacian in a single form can be written as del by del x A x plus del by del y A y plus del by del z A z into del V by del x A x plus del V by del y A y plus del V by del z into A z. This is the complete explanation of the Laplacian operator, and how it can be used for the different coordinate system. You can see here that del square V, it means del dot del V. Del dot del V means divergence of gradient of a scalar field, scalar V, and this is denoted as del square V, and this del square V can be written like this. In the same way, in cylindrical coordinate system, it is defined in the form of this, and in the spherical coordinate system, it is defined in the form of this. You have to remember all these transformation, all these changes, all these formulas to use in the different kind of studies in the electromagnetic field theory and antenna and wave propagation. As I have already mentioned that spherical coordinate system and all the operators which are used in the spherical coordinate system are the most important aspect in electromagnetic field theory and antenna and wave propagation. On the basis of these things, I have also mentioned some of the examples in my lecture. You can solve these examples, and answers are also given in my lectures. So, this is the complete lecture which was based on the very interesting and very important theorems and some of the very interesting operators like curl and Laplacian. So, thank you very much for this particular lecture based on the divergence, Stokes, curl and Laplacian. Thank you very much.